Yes, okay. We need to take a look at. Oh, why? Hold on. It's not functioning. Why it's not functioning? Still in the chapter 2, but part 2 in the wave function topic. Oh, now it's functioning, right? In the wave function topic, so we look at the slide over here. Here's a critical mathematical requirement. We look at the normalization concept. Remember, try to flashback. So we already learned the mathematical function of a wave function. The psi, okay, the psi equals to a sine kx minus omega t plus phi plus b cosine kx minus omega t plus phi, or we could use the Euler formula. The Euler formula, the psi equals to, sorry, e to the power of I naught equals to a something. Okay, instead of using this cos and sine, which is complicated, we can use the Euler. And then from the psi, we could predict the location of the electron using the psi square. Yeah, absolute psi square can predict the location of the electron. So before that, what we should do is that before we do the psi square, we should do the normalization concept. Okay, in total of the sum of all the probability must be equals to 1, such that if 1, exactly the electron is situated at certain location. So this is the normalization concept before we do the psi square. So if psi squared represents probability density, then the total probability of finding the particle somewhere must equals to 1. Probability is either 1 or 0, right? 1 is exist, 0 non-existence. So in total probability of finding the particle somewhere must be equals to 1. This is certainty. So this is normalization concept. We must total up all the probability and make it equals to 1. So mathematically, that means the integral of psi square, the integral of psi square, the total of psi square, the area under the graph of psi squared all over the place must equals to 1. Remember, area under the graph, the gray area, yeah, the probability of the electron to exist at certain area. So if you total up all the area under the graph of psi square, you will get equals to 1. So in total, the electrons exist is 1. So this is called normalization. So why does it matter? Because when you solve the Schrodinger equation, you get solutions with arbitrary amplitude. You don't know the amplitude, right? So you need to fix that amplitude by requiring normalization. In total must be equals to 1. Cannot exceed 1. Right? Because exist means 1. Non-existence means 0. So you cannot exist, you cannot more than 1 if you want an electron to exist anywhere. So the total probability must be equals to 1. Without doing this normalization, our calculation is not correct. So it also ensures the probability conservation as the wave function evolves in time. The total probability stays 1 if you start with a normalized state. So when we work examples, the first thing that we'll do after finding psi is normalize it. That is the first thing you do. Right. So let's see some okay, these are the notes. The normalization constant. I don't think we need to do the normalization manually. I don't think material technology students must do the normalization manually. This is what we call the normalization, right? We do the psi square. See, we do the psi square. Hold on. We do the psi square. Finding psi square. Psi square means we want to find the probability of the electron to exist at certain places. So we got this bell shape, and the total area under the graph of the bell shape must be equals to 1. So psi square from negative infinity to positive infinity over there, from the left-hand side of the curve to the right-hand side of the curve, the area under the graph must be equals to 1. This is normalization. Okay, from the right-hand side of the bell to the left-hand side of the bell, if we total up them together, all the area under the graph, We get 1. So this is normalization. Don't worry, I won't ask you to derive this equation, the normalization. I don't think the solid state physics for material type student need to do normalization manually, because this thing can be calculated using the computer instantaneously. You don't need to learn how to do it manually. Yeah. But in case you want to see how the equation looks like, well, you can just slide through the slide from step 1, 2, and 3, starting from the physical requirement. Okay, you total up everything must be equals to 1. Then do the normalization constant, which I don't think you need to learn this. This is just to show you the equations only. All right. So A is the amplitude, psi square equals to, must be equals to 1 over here. Right. Then solving the constant, we want to find A. But anyway, we look at this work example 1. Work example 1, the infinite well. Let's do a concrete calculations. A particle is in an infinite square well from x equals to 0 to x equal to L. A particle could be electron. Electron in certain places, maybe it is bound in the between the electrons and also between the nucleus. So it is bound in infinite square well from x equals to 0, x equals to L. So the wave function is psi n. Okay, psi n equals to c times sine of n pi x over L, and pi x over L. Where c is unknown and n is the quantum number. So we need to find c. Well, step 1 is set up the normalization integral. The integral from 0 to L of c squared times sine squared of n pi x over L dx must equals to 1. So this is step 1. Okay, so now how about step 2? Okay, this is step 1. Oops. How about step 2? We need to use the trigonometric identity. This is to show you how to calculate the c, because c is constant. We want to calculate the c. So step 2, evaluate the integral. The sine squared averages to 1/2 over a full period. So the integral gives c squared times L over 2. Okay, look carefully at the equations. So step 3, solve the c, find the value of c. So c squared times L over 2 equals 1. So c equals the square root of 2 over L. Notice c depends on L. The narrower the boxes require larger amplitudes to keep the total probability at 1. So the normalized wave function is square root of 2 over L times sine of n pi x over L. Now, this form appears constantly in quantum mechanics. So sometimes physicists has to memorize it. But you guys don't need to memorize it, because I won't ask you to derive this equation, just to show you. What I'm telling you just now, sometimes it doesn't make sense for you. But anyway, I just want to show you what the computer is doing behind the screen. Okay, the normalization, the infinite well, so on and so forth. Okay. So this form, also notice that for higher n, okay, for higher n, and this is the quantum number, the sine function has more nodes. It points where psi equals to 0, but the normalization constant stays the same. See? This is 0, this is x equals to L. So this is our ground state. Okay, N1 is our ground state. When the electron is not doesn't absorb any energy from outer, maybe from the heat, maybe from the light. So if the electron doesn't absorb any energy, it stays at the ground state. It doesn't, maybe it just vibrating or translating. It won't be excited to n equals to 2, 3, 4, 5, or 6. So it stays in its location, right? And the electron is bound with the pulling force of the nucleus and being pushed away by the neighboring electron and being pulled by the neighboring nucleus, because electron has negative charge, nucleus has proton. The proton has the tendency to pull the electron into the nucleus, but Doesn't happen because the electron also being pulled to the ideal nucleus from the neighboring atom. So the electron stays in its orbit. And please do not imagine the orbit is like a circular motion of planetary system. No, it's not like that. Okay. So what else? Let's see work example number 2, the Gaussian wave packet. Okay, the Gaussian wave packet. This is not the normalization example. Consider a Gaussian wave packet. Okay, psi equals to C times E to the minus x squared over A squared. Ni. This one, right? The first equation, the number 1. Okay, we have 4 steps. Look at the first one. Define the wave function. Consider Gaussian wave packet centered at x equals to 0 with width parameter A. We need to find the normalization constant C. We want to find the normalization constant C. So how do we define the normalization constant C? All right. So step 2, recognize this is a Gaussian integral. The general form is integral of e to the minus beta x squared dx. And it must be equals to square root of phi over beta. Right? What else? Hold on. Square root of phi over beta. Yeah. So here, beta equals 2 over a squared. Right? So how about the next step? The next step is step 3. Let us look at step 3.